Okay, in this video we are going to superimpose another curve over this, and it's gonna look like what I just had pulled up. It's gonna look like this curve right here, so that at any pressure you have your two volumes, the volume of your liquid and then the volume of your vapor, and that's what this curve shows, because the volumes in here don't exist. It's an artifact. That's the intermediate volume that I was talking about in previous videos. The volumes under here don't exist. You have a volume of liquid over here and then a volume of vapor over here. And up at the top, at the critical point, you have one volume, because when you have a supercritical fluid, the properties of the vapor and the liquid blend together and sort of become one. It's now one fluid. That's why we call it a supercritical fluid. What we want to do is create what Maxwell construction. We need to make pick a pressure or just a horizontal line on this graph, so that the volume or the area under the curve here and then here are equal. So let's go ahead and try and start coding this out. And for this function that we're going to make, we need two different things. We need our integrand and then our bounds for integration, because we're trying to find areas under a curve, and then how you do that is with integrals. This function we'll just call bounds, and it's going to return our volumes. So, and to get volumes, we need our pressure and temperature. Here are our volumes. And then we can use our cubic volume to unpack that. This is P T. Next, we need our integrand, which will depend on some specific volume, so we'll just call this function integrand. And that's going to depend on some volume, because our volume is on our x-axis. What we want to return from this integrand function is our pressure minus then our, where are we here? Cubic pressure function make that a lowercase v then. And now for this function, we need another import here. I just haven't imported it yet. Oh yes, I did. I forgot to mention, but we're going to use this scipy integrate, and it's a function called quad. And what that does is basically just take the integral. It's the simplest way to put it. So we'll just do quad of integrand, then v1, v2, and we want the first value, so 0, not those brackets. We'll do another quad, and then v2, v3, and we also want the first value from that. Now we just need to use the root solver, and to do that, we just need a function to supply to the root solver. And specifically, we're going to try and find a pressure that makes these two areas equal. So I'm going to go ahead and minimize this and then just open that up, make it easier. Okay, so I'll just define a function called some areas, and we need some vector and temperature. And then we use bounds in our function here with pressure and temperature. Then we unpack this into our areas, which are left. We'll just call them left and right. Easy enough. And the only thing we have left in here is this vector term right here. And if you remember, not that, we only have one pressure, just one line. So what we'll do is we'll just do P is equal to vec, and then just the first value of that. And our return will be just left plus right. Now let's test our function using the root solver. So we'll do root of some areas. Then our vector, we'll just do 10135. What just happened? Just do atmospheric pressure. And then in this root solver, we also have args, which is just our temperature, and we'll do the boiling point. So 373.5, right? Yeah. Okay, there we go. And it returned a pretty close value. Not bad. And I just want to take a second here and explain why this isn't 100% exact to my atmospheric pressure. So all of this work that's come from this notebook has come from the critical point. All of this that we have found and drawn up and coded out can all be found using just a critical point, which is how valuable and how important the critical point of any substance is. All right, so back to this. Now, since this is under x, the value that we're concerned with, we'll just do dot x. It'll just give us the x value. And since it's also in an array, we'll just do the first value in the array to get that out of the array. So now it just returns this value so that we can actually do something with that value. Since this root solver is returning pressure, I'm going to go ahead and just store it under a variable, just call it y, just to make it easier, since pressure is on the y-axis in pascals. So we'll just keep it consistent. And you'll also notice that to test out this root function, I just put in a temperature, but in this plot, you'll notice we have many different temperatures. So temperature is changing as well. See, all these plots correspond to a temperature. So we'll make temperature the argument a variable, and then we'll just put T. I'll just set it back to what it was for now, 373.5. Now let's use our cubic volume function, because now we're ready to start getting those volumes for our Maxwell construction. And if you remember, our cubic volume function returns 3 values. So let's unpack it into 3 variables. So we'll do volume of the liquid, and then the intermediate volume, and then the volume of vapor. There we go. And just because we don't really care about the volume or the intermediate volume, because it doesn't mean anything, it's not attached to anything, we'll just replace it with an underscore just so it doesn't confuse anything, and we'll just store it under that variable and we won't do anything with it. So let's try this. Let's print out our volumes here. I didn't shift enter that. There we go. Let's change this a little bit, see what we get if we change it. Let's do 7th and, I don't know, 600. Okay, awesome. Let's go ahead and get rid of that. Now we want to plot our two-phase envelope, and the way we're going to do that is by taking lists of values of the volumes and the pressure. and there's not going to be two lists. There'll be three because we have the volume of the liquid, the volume of the volume of the gas or vapor, and then the pressures. So we need three lists. So let's go ahead and do that. Let's just set up empty lists for our volumes and pressures. So we'll do volume of the liquid list. Volume of vapor. And we'll call this P list. There we go. There's all three of our lists that we're going to use and fill up with values. Take a look at this temperature. Remember I said we have a multitude of temperatures. You can see it here. We have multiple different temperatures. Also up here, all these different temperatures. So let's create a loop to iterate through and iterate and then we can append values onto those lists per temperature. So we'll do for T in np.linspace. Let's start at 250, something below the critical point or the freezing point and critical point of water, to let's say 475, so above boiling, and we'll go in steps of 25. You know what? Let's just do 450 back. All right. So there's our loop for T. And then what we want to do is so we'll go put these lists in here. And I'll indent for my for loop in a second here. To the last value. And we want all of this in our list. Or in our loop, sorry. Oh, I don't want to append to the last. We want to, so for P list, we want to append Y, V, vapor, we want to append the vapor value. And then the volume of the liquid, we want to append the liquid value. So now I want to draw your attention to this this root function. So this is our guess. And what I want to do is, we'll just call this guess. And then we will make our guess up here something. We'll call it, we just want to make something close. And so then each time through the for loop, we'll iterate another value for our guess that gets closer. So we're not just making an arbitrary guess every time, and we're getting more and more out of range of where we want to be. So I'll just make this guess as 1,000 pascals to start off, and then in here we'll just make our guess our new vapor pressure value up here, so our Y. There we go. Looks like everything works okay. Let's see, did I miss anything? Oh, I sure did. That's a big mistake. And then this needs to be Perfect. Look at VList here. We're good. So now let's bring down our plotting here. Make another one. There we go. And I'm going to go ahead and change these to plot. Now what we want to do, add another scatter on our subplot here. So we'll do plot dot add scatter, and our x will be y will be vapor volumes mode is lines. I'm sorry, my y is not that. It is plist. There we go. And then this is our vapor, or no, liquid part of the curve, so we'll just call it, yeah, we'll just call it liquid. Good enough. And this one will change to the vapor. We'll just call this vapor. Shift enter. And there we go. You can barely sort of see it. Let's change our range here. Range in the X, so range. Remember our X is log, so we'll do np.log. And I'll do something here so that it goes from the smallest volume, so we'll do min of V. I think that's right. No, I don't have capital V's in here, I don't think. To then, let's see. -2 should be good. There we go. Yeah, that looks pretty good. But you'll notice that these lines are not connected. The vapor is over here, or liquid, sorry. Liquid is over there, the one that's flashing, and then the vapor is this one over here. So we sort of need to connect those two lines together in that sort of curve. Not this. This one? No. In sort of this curve right here, that full dark line. And we sort of just need to bridge the gap between these. So we'll add another thing onto here. We'll call it vplot because it's just for plotting purposes. So then it'll be the liquid list minus the vapor list. And we want to use the reverse order of the vapor values because we're decreasing once we get past the critical point. So let's reverse these values. And how we do that is we go like this. You can look this up in W3 Schools, the indexing for lists and whatnot. W3 Schools is great. It has everything you could ever need, like syntax-wise, and it could help you learn Python if you're looking to learn. And then pplot will equal plist minus plist and then that same sort of indexing. That's not right, is it? Yeah, no, we're adding this. Sorry about that. Uh-oh. Oh, I had a capital P. There we go, that's much easier. So then this will be, our X will be vplot, and our Y will be pplot. And now this is just two-phase envelope. There we go. Okay, so in order to, I guess it is still just a straight line. Because we're assuming that temperature is increasing linearly as we go across this curve, but it's actually not. So the way we want to do this is change our t as it's spaced out. So we'll start, let's start from 0. From 0 to, we'll say about 10. 10 in, and then just a ton of points. So like 400 points, 600 points. We will change this to x and make it depend, and make t in our function depend on x. What we'll do is we'll have t equal to our critical temperature minus 250, which is our initial value in our plot here, 250. Yeah, 250 Kelvin. And multiply that by some sort of function or graph that has temperature decreasing as it gets closer and or as it gets higher and higher, decreasing in its steps as it gets higher and higher. And the first thing that I think of is an exponential function. Sort of, let's go to Desmos. Yeah, here we go. So e to the x. That's what we want, is like this part of the graph, but then up here towards that side. So if we do, let's see, x to the negative, or e to the negative x, that's not it. There we go. We've sort of got it flipped over there. So what if we do negative e to the negative x? There we go. As it gets greater and greater, it starts to taper off in how it increases. And now we just need to get it above the origin. So to do that, we just put in like a 1 here or a 2. But in our case, it'll be, so we'll just do 1 minus that put this in parentheses. And then we'll do like whatever our critical temperature is. So we'll just say like 500 minus 250, because 250 is our starting point. There we go. Now it looks how we want it to look. We go up to a really, really high temperature and then start tapering off. And all we need to do is use this function. So we'll just do, here we have it here. So we have our critical temperature minus 250 and then times 1 minus np dot exponential of of x, negative x rather. And I think that's good. Let's try it. Uh-oh. Oh, it's saying this is not a float. God, I'm really bad at that. I never do that. Float object is not callable. Okay, there we go. I had to drop this down to about 8 for it to work. It was just given too much. Let's see if these work. There we go. And now you can see it's a curve. It looks awesome too. There's our curve. All right, I hope this series of videos was beneficial to you. And just to go over everything again, all we did was take the van der Waals equation of state and the compressibility factors, or critical compressibility factor, and the critical point, and we used just that to then find all of these different isotherms and then the Maxwell construction, which is pretty amazing. So thank you for watching.